Okay, so now we come to Einstein's starting point, the two postulates. In other words, we come now to the famous June 1905 paper entitled On the Electrodynamics of Moving Bodies. And this is the paper where he introduced his special theory of relativity. And sometimes we get the idea that, again, he was 26 years old, he was a clerk at the Swiss patent office. This came out of nowhere. But if you actually look at it, he had been working in this area, thinking more and more deeply about these things for 8 to 10 years at least. We see this in some of his correspondence, and unfortunately we don't have any notebooks from that time period where he was working on this. We do have some of his school papers and things like that, school notebooks, but nothing specifically on this. But he does mention it several times in his correspondence with friends and with his girlfriend Mileva, and then later his wife. And so we know he was thinking about this for a number of years. And in fact, later on he described it as this psychic tension he felt, that this was an area, whatever, and we'll get to sort of what this means here in a minute. This was an area where he saw certain what he called theoretical asymmetries, and he could not figure out, so sort of contradictions. He could not figure out what was going on and what was going wrong. He just felt there was something wrong there and actually couldn't see it until a few weeks before this, in April 1905, he went for a walk with one of his friends at the patent office, Michael Besso. Einstein had actually helped Besso get a position at the patent office the year before or so. They'd been friends before that and often went for walk and talks, as it were, during lunch hour or whenever, and just they discussed physics. And one of the things evidently they discussed was this. And so one day he came back and he told Besso, "I've solved it." And the famous phrase he later said was that time is suspect. In other words, the normal notions of time that physicists and pretty much everybody had for years and years and years, something was wrong with them. That's where the contradiction lay, or the solution to the contradiction that he felt. So we need to sort of figure out what's going on with that. What are these two postulates? What's going on on the electrodynamics of moving bodies? And also note that Einstein was not the only person working on this. In fact, there were some very well-known, respected physicists working on it, such as Hendrik Lorentz and André Poincaré. In fact, two of the leading physicists of the time, Lorentz in the 1890s had extended Maxwell's theory of electromagnetism in a number of different directions, expanded it, and then Poincaré and Lorentz worked together to a certain extent in the years right before 1905 to put it into very sophisticated mathematical formalism. And it was a very detailed theory. So again, it wasn't like Einstein just came out of nowhere and no one was working on this and he had these great insights, but that other people work on it. And in fact, Lorentz and Poincaré came up with some of the same ideas that Einstein did in terms of his theory of special relativity, but from a totally different direction. And actually a much more complicated way of deriving it. And Einstein's way, his approach to the matter, was much simpler. In fact, it was so simple in some respects, people dismissed it just because of its simplicity, and they sort of preferred the more sophisticated, complicated theories of Lorentz and Poincaré. So in fact, it's a benefit for us, though, because the basic concepts and math involved in Einstein's theory are such that we can actually teach it in a course like this and understand it, even if we don't have that more sophisticated mathematical background. So, what was actually in this paper? What's this idea with electrodynamics of moving bodies? I hope you, especially those of you who are doing the quantitative approach, that you read the paper. Again, I don't expect you to understand it. Sometimes you hear it said that anyone should be able to sit down and understand this, sort of if you have a college-level education or something like that. I don't think that's true. There are a fair number of equations in it, there's a fair amount of assumed knowledge about physics and math and so on and so forth that you really need to get an understanding of it. But for our purposes, even if you're doing the qualitative approach, it's good just to skim through it, look at the various section titles, see how he organizes things, read the introduction, read some of the conclusions, and get a sense that way. So electrodynamics of moving bodies deals with electromagnetism here. Dynamics refers to forces, so we're talking about sort of electrical forces involved in moving bodies, just objects moving like that. So what was Einstein's approach? Well, it was very different from the approach of people like Lorentz and Poincaré, who were trying to build very detailed models of things like electrons and the so-called ether, which is the medium or seat of electromagnetic forces, and light waves and things like that, of which we will talk more later. Einstein, if you look at his paper, he starts off with, first of all, just a statement of some things that were bothering him, these so-called theoretical asymmetries. And one of the big ones was simply, if you take a bar magnet, so say we've got a bar magnet north and south, and then you have a coil of wire here. So here's our magnet. Here's the wire. And today we'd say there are electrons in the wire, so there are charges there that could move around the wire if we attach it up to a battery or something like that. But also, from Maxwell's theory of electromagnetism, that if the magnet moves towards this coil of wire, we know the magnet generates a magnetic field around it in some sense. If that magnet moves toward that coil of wire, the theory said that it would generate an electric field in the wire, in and around the wire, and therefore the charges in the wire under the influence of that electric field would start moving. In other words, more technically what happened is, as the magnet moves here, the magnetic field in the vicinity of the wire is changing, and that generates the electric field, which then pushes the charges around the wire. In other words, you get a current in the wire. Okay, so Einstein says, great, that's fine. But that's if the magnet is moving. If you say, let's consider a different case, let's keep the magnet stationary and have the wire move toward the magnet. Okay? You get the same result. The physical situation is the same. One is moving toward the other. You get the current in the wire. But the theory in that case gave a very different explanation. It said in that case, as the wire moves toward the magnet, and there's a magnetic field around the magnet here, that magnetic field acts directly on the charges in the wire, which are actually moving toward the magnet. The whole thing, obviously the charges in the wire are constrained to move in the wire, so the whole thing is moving toward the magnet. And the theory said if you have a moving charge in a magnetic field, there's a force on it, so it starts, again, circulating around like a current. So physics, for our purposes, is useful there to understand, but the most important thing is physicists were giving two different explanations for the same thing. And in this case here, they're saying it's the magnetic field that actually is pushing the charges around the wire. If the magnet, though, is moving, it's an electric field that's generated that pushes the charges around the wire. And Einstein found this rather bothersome. He did not like it at all. He felt there should be one physical explanation, because it really shouldn't matter whether the wire is moving, the coil of wire is moving toward the magnet, or the magnet is moving toward the coil of wire. So that's one of the theoretical asymmetries he highlights at the very beginning of his paper, his June 1905 paper. And by the way, I can't remember if I mentioned this or not, but he had his conversation with Besso in mid-April or so of 1905. Within 6 weeks, he'd published the paper, or finished the paper and set it off for publication. So again, you see that he had been mulling these things over for a long time. They'd been percolating in his mind, in a sense. And so once he got the key insight, it didn't take him long to work out some of the key implications. So if you look at the actual paper, it's divided into two key parts. And the first part, he labels a kinematical part. And then the second part, actually, which we'll write up here, it's an electrodynamic part. where he takes some of the results from the first part and applies it to Maxwell's theory and a few other things in terms of the theory of electromagnetism. We're not going to go into the details of that because the key things for us, these two postulates in particular, really come from the first part here. Kinematical part, what does that mean? Well, kinematics just really deals with things in motion. It doesn't worry about forces and things like that, so it's not worrying about this dynamic stuff here. It's just saying, let's go back almost to first principles. And let's make sure we really understand how we measure things in motion, velocity and length and time. So very simple beginning, and that's, again, one reason why Einstein's approach to it was dismissed to a certain extent, because it seemed like it was just almost trivial stuff he was trying to do. So this kinematical part here, what was he doing? What were these two postulates? Well, the first postulate was the principle of relativity. And this postulate goes all the way back to Galileo in the 1600s, if in other forms, perhaps even before that. But certainly Galileo put it into its most famous form that influenced later thinkers such as Isaac Newton. And essentially, the basic idea is, for Galileo, he imagined ships on the ocean. If you have two ships on the ocean and the water is fairly calm, air is fairly calm, but they're in motion with respect to each other, if you're on one ship, the question is, are you moving or the other ship is moving? In our day, maybe cars or trains. If you've been on a train before, another train is right next to you, you see all of a sudden things are moving if you're stationary at first, and then you're not sure, is your train moving or is the other train moving as you look out the window? So the principle of relativity says that motion is relative, that there's no absolute, term we'll use later on, absolute frame of reference. Again, we'll explain that in more detail later on. But there's no way you can really tell that you're moving versus something else is moving unless you specify it. You can say, okay, compared to the floor here, I'm moving or not moving. But of course, I could think, well, the floor is attached to the surface of the earth, and the surface of the earth is moving. So in that case, with respect to the center of the earth, the whole floor and me and everything else, all of us, are going around the center of the earth. So that the principle of relativity says that if you really think about it, you can't tell whether you're moving or not. You can say, with respect to this or that, I'm moving, but then maybe that person over there, I could say they're moving, but they might say, no, I actually see you moving. More specifically, and this was the thought experiment we did early, the first thought experiment in week 1. If you're in a railroad car and you have those various items in there, and to see if you can actually do an experiment or put them together in some way to tell whether you're moving or not. And so a more precise version of the principle of relativity is to say that there's no experiment you can do in a situation like that will tell you whether you're moving or not. Another way to say this, there is no state of absolute rest. You can't define any frame of reference that you can say is absolute rest to everything else, and then you refer any given motion to that state of absolute rest. So, principle of relativity, this was well established in physics. It wasn't anything that new, but Einstein said, okay, let's take that. But then he also said there's a second principle coming out of electromagnetism, and relates somewhat to the bar magnet and coil example I gave in a minute. So he said, electromagnetic theory, we now know, says a few different things. It basically seems to violate the principle of relativity. Again, the coil and magnet, it shouldn't make any difference whether the magnet's moving or the coil is moving. And in actual fact, experimentally, it doesn't. You still get the same current around the coil. And yet physicists were explaining the two situations in two different ways. And so Einstein said, if we really believe in the principle of relativity for everything, then that shouldn't be so. And so that was one thing, the coil and the magnet. But also electromagnetic theory said that light was a wave. And that also led to things where it seemed the principle of relativity was not valid for electromagnetic theory. In particular, and next week we're going to, or I should say this week, we're going to explore it more in some of the video clips. What did it mean that light was a wave? This came out of James Clerk Maxwell's electromagnetic theory, showing that there were electromagnetic waves and vibrations that traveled along through the so-called ether, which was the medium through which light traveled. Waves have a medium. Water waves travel in water. Sound waves travel through the air. Light must have some sort of medium through which the electromagnetic disturbance travels that makes up light, and that was typically called the ether. Now, the idea of the ether goes way back centuries, actually, but at the time of the late 1800s, early 1900s, the idea of what was known as, we'll use the full term here, the luminiferous ether was the idea of a medium that was everywhere, okay? Because it had to be. Anywhere you can have light, even in a vacuum. You can send light through a vacuum, and therefore there had to be a medium that carried those light vibrations, as it were, those electromagnetic vibrations that made up light waves. And this ether, if you think about it, was had very interesting properties because on the one hand, you can just move your arms around and things like this, and everything's, seems to flow right through it. There's no drag or friction that we can tell of. And yet, on the other hand, physicists knew that for a wave-like phenomenon, if you have very high-frequency vibrations, and light actually is a very high-frequency vibration compared to most anything else, that only occurred when you have really stiff, rigid type of materials. Think of like a really stiff, rigid metal bar versus something a little more pliable in terms of if you bong it with something, the type of vibrations you will get. So the ether, on the one hand, seemed like it should be very stiff and rigid so that it could generate or carry those electromagnetic waves that were light. And yet, on the other hand, it seems like things can just pass right through it. So there are a lot of mysteries about the ether, and that's what people like Lorentz and Poincaré had really been working on for the last 15 years or so when Einstein came along in 1905. So how is this a problem, though, for the principle of relativity? Well, if the ether exists, and it's really like the background of the universe, really, that everything sort of sits in the ether is all around us, then that could act as an absolute frame of reference. I could say, am I moving or not? Well, if I can just measure my motion with respect to the ether, I could tell, hey, I'm moving. In other words, the ether would be an absolute frame of reference, a frame of absolute rest, and all motion then could be referred to this supposed ether. And that would go against the principle of relativity. And more specifically, in terms of what Einstein was doing with his two postulates here, he had the principle of relativity. The second postulate that he stated, second principle, going along with this, just to be precise, was what he called the principle of light constancy. The principle of light constancy. And what he suddenly realized was, because it seemed like these two things were in contradiction with each other. The principle of light constancy, which we'll explain as we go along this week, get into that a little bit more, really is a statement of the fact that light is a wave and the so-called luminiferous ether should exist. This light-bearing, luminiferous being light-bearing ether should exist. And yet that seemed to go against the principle of relativity, another well-established principle. So you had two very well-established principles in physics that seemed to be in contradiction with each other. And that was what really bothered Einstein. And so what we need to start figuring out this week and beyond, is exactly what does this mean here, this principle of light constancy, and how does it fit together with the principle of relativity, or how it doesn't fit together with that, and then how Einstein put the two together and said, actually, they're not in contradiction with each other, But if you assume they're both true and you work out some of the implications, you start to get some very weird results. And these are the results that you see actually in the kinematical part of his paper on the electrodynamics of moving bodies, where things like length and time aren't defined as we would normally think them, in the sense that they're not absolute. They're relative, the relativity of lengths and times. Simultaneity and clock synchronization becomes problematic. And in fact, another point here, if you read this, note the examples he uses. He talks about trains and clock synchronization. These were not just philosophical notions or problems that he's working with. In the patent office, this was cutting-edge technology in terms of synchronizing train schedules, synchronizing clocks between different stations, and so on and so forth. There's no direct connection that we can point to between his work at the patent office and some of his ideas. Unfortunately, all his patent work was destroyed after about 14 years, I think it was. That was just the normal procedure, that they'd keep the records for 14 years and then get rid of them. And so we don't actually have really any of the patent applications Einstein worked on, but we do know the types of patents that were going through the patent office all the time. And a lot of it dealt with issues of clock simultaneity, clock synchronization, trains, and so on and so forth. And so it's interesting and important that Einstein is using some of those examples in this paper. So again, the overall context of what he's working with, not only the context of physics and the key problems of the day that people are working on, but also the technological context in which Einstein was embedded, in a sense, in the Swiss Patent Office. So as we move ahead here, our goal will be to learn more about this principle of light constancy and a little bit more about waves, so we can understand this and then see how that relates back to the principle of relativity, and how when you put it all together, you start getting some very weird results.